Welcome to my Autonomous Mobile Robotic Lab series. In this series of videos, I will be documenting the build of an autonomous robot and exploring common controller algorithms such as PID, potential fields, and A-star. We will explore both choosing and building hardware capable of meeting our objectives, and the mathematics and software algorithms that will make up the brains of our robot. In this first video, we're going to take a look at various robotic platforms and talk about the requirements we have of our robot. We're then going to take a little bit of a deeper look at the Pololu 3Pi Plus, the robot that I've chosen for this video series. We will also create our first program on the robot, using the robot's wheel encoders to drive the robot forward exactly 12 inches or 30.5 centimeters. We'll then learn how to control the dynamics of the robot and lower the speed of the robot to bring it to a graceful stop. We have a lot to explore in this video, so let's jump right in. The first topic I want to discuss are the requirements we have for the robot. There are many types of robots in the world, and they are specifically designed to solve a certain problem. Our task is to design a robot that can operate completely autonomously, meaning that we don't directly control it, it acts independently. Our robot needs to be able to navigate to a goal location in an indoor environment, and along the way avoid any obstacles that might be in its path. In addition, these obstacles are dynamic in nature. They're not static. They can move around. People, pets, etc. Our robot has to be able to deal with furniture moving, people moving, all kinds of changes in its environment. I want to take a moment to look at some of the various robots here that I have in front of me and use them to help describe what we're trying to achieve with our mobile robot and what we're looking for in a good robot design. These robots here are all holonomic robots, which means that they can achieve turning to any angle at any given moment. So if you think about a modern car, if you have to parallel park, it takes multiple steps to do that. You have to pull up next to the car that you want to park behind, and then you have to cut your wheels and back in, and then if you did it really well, you can do it in a third step where you just kind of like even out and pull forward, but maybe you had a few more shifts in between. This is because the car is not capable of operating past a certain number of degrees that it can turn at any given moment. A robot like this, with what's called a differential drive, can use its wheels to turn the robot at any angle at any moment, meaning that it can achieve any location at any moment. And that's going to make our life for our coding, our algorithms, a little bit easier. Now, we don't want our robot to stop and turn and then go. That doesn't look very smart. We want our robot to make nice, smooth kind of driving transitions, and it will, because our algorithms are going to be smart. But the important part is that by being holonomic, it allows our algorithms to be much less complicated because we don't have to plan for that trajectory or multiple steps to accomplish the end goal. Another trait that these robots share, or except this one because we haven't put it on this one yet, is that they have ultrasonic sensors. Some have more than one, and some have one here that's maybe mounted on a servo, and we're going to talk about that more in later videos. But these sensors are going to be the eyes, but actually more specifically the ear of our robot. So our robots are going to operate much like a bat. These sensors emit a high frequency sound, hence the ultrasonic, which then can bounce off objects and be heard by the same device. The amount of time, or the time of flight, that it takes for that sound to hit something and bounce back can be computed as a distance to the object that it bounced off of based on how long it took to come back to the robot. These little sensors literally will give us just points in space when we do the math as to how far away something was when sound bounced off of it. We can use that information to construct an idea of where obstacles are in the world, things that we need to avoid. We don't know anything about them other than a sound wave bounced back. We don't know the color, we don't know the shape, unless we hit it with enough pings that we can kind of define a shape, and maybe we'll look at that more in a mapping piece of this after. I might kind of take it further. But for right now, what we're really concerned with is I got a ping back and it's at a certain distance, so I know there's something there. I don't know much about it, but I know there's something there. Another important aspect that these have are wheel encoders. So actually this one does not have wheel encoders, but the other three do. Wheel encoders is something we're actually going to talk about in this video. So wheel encoders are basically the ability to map how far the wheels turn. This is done either optically or magnetically with a Hall sensor and a magnet. In this case, what we get is a number of clicks per wheel rotation. We can then use that, knowing the circumference of this wheel, to map exactly how far that wheel has turned. When we do that, we can actually use a lot of trigonometry to extrapolate out how far this robot moves, at what angle it turns based on the difference between how far the two wheels turn, and where we want to go. So we're going to spend a lot of time actually building out those algorithms purely on these wheel encoders. Now, there are other sensors there that can help us. These have a compass, accelerometer, gyroscope, and those sensors are very helpful as well because they can tell us things about the inertia of the robot and what direction it's pointing in. So the combination of those sensors is going to allow us to position this robot in space with a fair bit of certainty, although there's going to be some error, and we'll discuss that as we go through. While I'm going to be using these robots in this video series, you can use any differential drive robot. I actually have a video here where I build this robot as I was evaluating it for this process, and I really do like this robot, and it's a little bit cheaper than, you know, say these robots here. The one kind of failing of this robot was that it didn't have the wheel encoders, and more so it was going to not be easy to add them. So I actually like the chassis on this thing. It's actually very thick acrylic. It's actually pretty well put together, but unfortunately they did not cut out the slots for the encoders in it, which means if I wanted to make this and have a video series for people to follow along, they would have had to have found a way to do that themselves. An alternative, which I did explore, and I'm going to provide the link for this guy down below because that one was in the other video and I didn't have this one yet. In an effort to use the components from this one but have wheel encoders, I basically bought another one of these because they were so inexpensive, and use all the components on a different, I think it was like a $15 chassis that came with the chassis, the wheels, the DC motors, and then I used all the components from here, the Arduino, the shield, the battery, the lithium battery, ultrasonic sensor, and the servo. I did have to buy the encoders separately. I think they were like $7 or $8, but it had the slots for them in this one. So this was completely assemble yourself, screw it together. I didn't have to modify it in any way. It's differential drive with just two wheels. With this one, there's always the risk, and I would say it's a pretty significant risk, that you're going to introduce more error as it turns because you have four wheels and it's not going to pivot as cleanly on a single contact patch on each side as this guy will. For that reason, I really do like this chassis a little bit better, although this one is of a much better quality. But you can use any kind of robot like this. You're going to have to tune it different. So obviously the weight is different, the wheel's diameter is different, you know, the speed of the DC motors is different, how they respond is different. There's going to be lots of differences, but these are all things that you tune out. The algorithms that I'm going to discuss, starting today with how to convert the clicks of the wheel encoders into a distance like centimeters, that's all something that comes across. When we do potential fields, all those algorithms come right across. The algorithms are the same, the tuning is different. You can actually use, there's other robots like the Zumo from Pololu. If you want to be really ambitious, there's also the Balboa, which is behind me. This one is an actual standing robot, so you have the additional challenge of having to balance it as it moves around, but it would absolutely work for this. You would have to just mount the ultrasonic sensors on it. You can also lay the Balboa down. There is a kit sold called a stability conversion kit by Pololu, and you can see it here on one of mine with the ultrasonic sensors mounted on the front. So keeping in mind that we can use pretty much any robot and follow along with these projects, I want to now talk a bit more about the robot that I will be focusing on, which is this little guy. I should mention that I'm not in any way affiliated with Pololu, and I've purchased my own equipment. I just really do like this robot for the problem we're trying to solve. It is very well put together. The gear motors are excellent. I have had a bunch of Pololu robots over the years and they have all worked extremely well. I like that this robot is assembled for the most part, except for the few sensors that we're going to add. I've included a link in the description that you can use to get the robot if you want to follow along with the videos. And as the videos progress and we start adding components to the robot, I will be adding links in those videos as well. I also want to note that the pictures of the robot you're seeing here and the previous shots were taken using the same exact robot, but an earlier version of it, and I'll just be building a new version as we progress. Unboxing the 3Pi Plus 32U4 robot. This is a standard edition. Notice the 30:1 on the gear ratio for the motors. There's also a Turtle edition and a Hyper edition. The Turtle edition is half, or actually slower than half, the speed of this one. Turtle edition is a 75:1 ratio. This is 30:1. The Hyper edition is twice as fast as this at 15:1. The robot comes just packaged pretty simply. There's not much here. You just get the robot itself and these two clips. So these two clips are actually intended to be used as alternative mounts for hardware if you take the ring off of it. You have the bumpers in front, the wheels here on the sides, the battery covers here. I have rechargeable batteries. I highly recommend that you do the same. They're AAA in size. This is a differential drive robot, so we have our two drive wheels and a caster wheel. On the top here we have a LCD screen. We're actually going to be probably removing that, but I'm going to use it for this demo. We have a power switch on one side, reset, and 3 buttons below, A, B, and C. I'm going to remove the LCD screen here momentarily to show that there's a buzzer underneath here, so we can use that to play sounds. And we're also going to use that jumper header to attach some hardware. So I'm going to look at adding servos and ultrasonics on top. There are a few more features here worth mentioning, such as the line following sensors, but what I really want to drill into now is the expansion ports that are available to us on this robot, since we're going to need range finding sensors such as the ultrasonic ones that we discussed, and ideally I want to set this robot up with a small servo and an ultrasonic sensor. Now the expansion ports that are available to us do allow you to get to pretty much every pin that is available on the Arduino Leonardo compatible 32U4 microprocessor. However, you have to solder on the headers in order to do so. That is something I'm trying to avoid, or would like to avoid, because I want these videos to be focused on the programming of the robot and a little bit of the hardware, but I don't want to add any additional bars to entry. But luckily we can avoid all of that by removing the LCD and using the header underneath. There are 6 pins available there, as well as 5-volt connection and ground. The only gotcha is that there's only one 5-volt connection, so we're going to need to use it to power multiple devices. So our next step is to set up your development environment so that you can create software and flash it onto your robot. I've come to the Pololu site here to find the user guide for the robot, as we'll be using it quite a bit throughout this whole lab process. On their site here under Robots, you can see there's a 3Pi option, and then I've selected the newer 3Pi Plus. One thing I want to point out while we're here is that there are a few versions of the robot, and there are both assembled and non-assembled ones. I highly recommend the assembled ones. They are only about $10 more. I want to take a moment now quickly to look at the 3 versions of the robot they have here: the Turtle, the Standard, and the Hyper Edition. For our projects here in this lab, I recommend either the Turtle or the Standard Edition, and I think I would recommend the Turtle Edition over the Standard Edition. The videos I've been playing of the robot doing obstacle avoidance and go to goal behavior with the cats jumping in front of it, that's actually a Turtle Edition, and I don't feel that it's very slow. I feel that it's a reasonable speed. The Standard Edition is a little bit more than twice as fast. It's also harder to control when it's moving very fast. So I'm going to go ahead and click on any of these. It doesn't actually matter which one for the sake of finding the user guide. I'm going to scroll down to Resources, and here is the user guide here. Please get acquainted with this user guide, read through it. There is a lot of very useful information in here. You can see there's information on the headers, as I mentioned earlier when we were discussing the LCD header that we're going to use. There's also additional information here that lists every pin on the 32U4 and the corresponding Arduino pin names, and how those pins are used by the 3Pi Plus, along with some notes. Where I want to focus now is on the programming the 3Pi Plus part, and specifically the installation of the software. If you've never programmed for any Arduino-based microcontrollers before, you're going to have to make sure to install any Windows drivers you might need if in fact you are using Windows, and setting up your Arduino IDE in order to work with the 32U4. Now the 32U4 has a specific software that is provided by Pololu that you can follow this guide to download and install, at which time you will be able to then see those boards in your Tools Boards menu and select the Pololu A-Star board. Another important step is to install the Pololu 3Pi Plus Arduino library. This is a library of code that's been made available by Pololu to help with low-level control of the hardware. In order to install the library, you're going to go into your IDE, open the Tools menu, select Manage Libraries, search for the 3Pi Plus. Once you've installed this, you'll be able to use their libraries in your code. Please also explore the library documentation to learn more about the library and how to use it. So getting started with the code portion now, I've opened a blank skit in the Arduino IDE, and I recommend using the Arduino IDE that you install on your computer and not the cloud-based version. I want to take a moment to just look at the library as well that they've provided. So if I go over to my Finder here, a couple things I want to point out is just once we start flashing this device, if you ever want to return it to its stock form, they've provided that demo program here. And there's a lot of other example programs here that can help a lot when you have questions about working with specific hardware. So for example, there's an Encoders one right here that we're going to use. In fact, while I'm here, I'm going to grab this code here, and I'll describe a little bit more about what this code is as I paste it in, but it's going to save me a little bit of effort as I do. I want to just note too that I'm not going to follow this verbatim. However, it is worth coming back here and checking this out. For example, I'm in this demo not going to go through worrying about errors that might be produced by the encoders, but you should in a real program. And there's a good example here of exactly how you should do that. All that said, I'm going to just close this, and we're going to come over here to our own skit, and we're going to paste in this code. You can of course, type it in or get it from any of those other examples. But what we're doing here is we are including that library, the Pololu 3Pi Plus 32U4 library, and the namespace that goes with it, which then allows us to just refer to the classes within that namespace. Now, these are different pieces of hardware that we intend to use, and we're using their library in order to avoid having to write that low-level code ourselves. For today, we're very specifically going to be working a lot with the encoders. I actually don't need the LCD, so I'm going to remove that. I will, however, be using the buzzer and the motors, and at least one of the buttons. I think I'm going to remove button C because I don't foresee using that. To get started, I'm going to go to Setup here, and it's worth noting, in case you're not familiar with Arduino, Setup runs once when you either start the device or reset it. So basically when power is applied or a reset is applied, you run setup once. Then the loop continually runs throughout the life of the program. One thing that I want to set up is my serial connection so that I can use my serial monitor. So we do that by typing serial begin and providing a baud rate at which we want to send information to the serial monitor. I will show this on the serial monitor in a few moments when I actually use that to display some output. So for right now, we're going to leave that like this. I'm also going to add a delay here. Now, I normally recommend against delays in general. However, in this rare instance in setup, I do like using it. Oftentimes, although there's not at the moment, there's some hardware that might need to calibrate, and the delay provides for that. But I also like to just have the robot wait a second before it runs away when I say press reset or something like that. So I've just gotten in the habit of adding a second delay there. Another thing I want to do is I want to have this thing play a note when it's starting, just so I can audibly hear that yes, the robot is kicking off, and I know that that means that I am on my way and running my program. So it's just more to appease the human who is coding it to kind of know that things are happening than anything else. So that's all I really need there for now. And for this very first deployment, we're going to keep things super simple. I'm not even going to bring the encoders in just yet. I just want to put some code in so that we can see the motors work. But to make it so the robot just doesn't run away endlessly, I'm going to make it so that the motors will run if we press button A. So the way that we do that is by using the button that is provided there. Button A is the button that we've brought in, and we're going to use the isPressed method. And when we press the button, we want the motors to run. So to do that, we use motors, and set speeds is the method that we're going to use. And I'm going to set mine to 100. I have the standard edition. If you want to try it a little bit higher than that, you can. If you have the Turtle edition, you could go higher than that for sure. If you have the Hyper edition, I would actually recommend going slower than that. Anything less than 50 is questionable for stalling. Definitely say less than 30. Depends on the motors themselves and the gear ratios and things like that. But don't expect the motors to be moving if you only provide a very low value of, say, less than 30, and possibly even less than 50 could be a problem. Now, the only other thing we really have to do here is make sure the motors are not running when we are not pressing the button. So I'm going to provide an else here, and I'm going to set the speeds to 0 when that is the case. So I believe this is pretty well done. The only thing I want to do is I'm going to add something here for the serial monitor, more so that it can show exactly how that works and you can get used to using it. So to do that, you do serial print, and if you do print with LN, it'll do everything on a new line. So what I'm about to type here will get a line of its own, and then the next thing that gets output will be on a separate line. If you leave off the LN, it will just keep putting things on the same line. You're going to want to do that later, as you can't really concatenate in here very easily. For now, we just want to know that our motors are running, so let's say that. So motors running, and we are good to go. Now, you have to usually save this before you run it, so go ahead and do that. And you also should check it with a verify. So we're going to click the check here. It's going to compile the sketch. It says done compiling. It looks like everything is good. I'm going to bring over my serial monitor here, and I want to point out that it's at 57,600 baud. So that matches what we have here in our serial begin, which will allow communication between our computer and the robot. At this point, we're ready to go to try this out. Now, one thing I want to note is that your motors will not run if your power on the robot is not on. If you just plug in USB, you will have power enough from the USB connection at 500 millivolts to power the actual 32U4 chip and the electronics. But the motors themselves only run off of battery power. So the little power button that's on the kind of bottom left-hand quadrant of the robot, that needs to be pressed, and the blue light that's directly above it needs to be on in order for your motors to actually spin. You can upload programs and run them without your motors being on, or your power being on, I should say, as long as the USB is plugged in. But be aware that things that require the extra power, like your DC motors, will not be running. To deploy this now, I click the upload, and it says it compiles the sketch and it uploads. I should hear my beep. There it is. And now that it's on, my power is on, I should be able to press A. Let's get our serial monitor ready here. There you go. You can see that all my motors running up here. And if I clear this, you can see that while I'm not pressing the button, they do not show up. But if I press the button, there you go. And the robot moves. So success for our first program. Now, let's go ahead and bring the wheel encoders into this. We're also going to explore just good robotic, and specifically robotic on Arduino, programming practices. So one thing I want to address right away is this. So very often you will see loops in Arduino programming where there's some sensors to check or something to do or LEDs to light up, And in order to make that happen for the time you need it to happen, a delay is added. Now the problem here is that when you get to a delay in this program, it literally sits here and does nothing but run this delay. Any other work that was part of this loop does not happen, whether it's, say stopping the motors from running or looking at the sensors to avoid crashing into a wall. So we want to avoid that at all costs. What are we going to do instead? Well, the first thing we're going to do is create methods to encapsulate everything that we're doing. Now, this one's a very simple program. We're just looking at the wheel encoders, but obviously this is going to grow over time. So for right now, let's just call this check encoders, because we're just going to have this method check the encoders. It's also going to respond to them, but that's fine for now. And we're going to need to call this from our loop, so we'll go ahead and add that as well. Now that we have this, what I want to do here is, instead of worrying about delays to separate how often I check my encoders, I'm going to use the built-in timers that are in the microcontroller. And you can do that very easily by using the millis function that's provided. The millis function gives you the amount of milliseconds that have elapsed since you turned on the device. So kind of like the epoch time, where the timestamp that we use in computing, where that started on January 1st, 1970, well, this just starts every time you start the device. Now, to do this effectively, we need to store the information. We need to store the current time. We need to store, say, a previous time that we might have checked something. And we need to know what the interval of time is that we care about, that we want to wait before we check it again. So let me go ahead and create a few global variables here in the global space that we're going to use for that. So the first couple are going to be unsigned longs, and these are going to represent both the current time, so we'll say current millis, and also the previous time that we say checked for this thing. Now, you might have many of these in your program as your program evolves, because you might have ones for checking the encoders, and ones for checking the ultrasonic, and ones for how often you check the speed of the motors. So you'll probably end up with multiple versions of these, and they'll probably incorporate the names of what they're checking. Since we're only checking the encoders here, I'm just sticking with current millis and previous millis, but you might adapt that in the future. The last one here is going to be a constant, because we're not planning on changing it at runtime at all. And we're going to call this one the period, because it's going to represent the amount of time that we're looking to wait before we do this again. I'm going to start off with 50 milliseconds here. Now, we might have to adjust this. One of the most interesting parts of programming in robotics is that you're dealing with the physical world. And if I say, let's say I make this 500, right? So every half second I check the encoders. The problem with that is that if I want to go 12 inches, I could very well overshoot my 12 inches by a pretty significant margin, because I'm not checking the encoders often enough to know that I actually went the 12 inches. However, I could make this too small a number. I could say, well, why not check it every millisecond? And then my code to check the encoders is running far more often than it needs to, and it's taking up the valuable time of the processor from other things that might need to run. There's always a balancing act in doing this, and a lot of it you learn with experience for different types of hardware, and a lot of it comes from thinking through the requirements and the probable issues that you could run into. Tuning a robot in the physical space is one of the greatest challenges of doing robotics programming. So now that we have these, we're going to take our current millis here, and we're going to set that equal to the millis that's recorded. So we're going to do that every cycle, which this is going to happen as fast as the loop can get through all our code. So this is going to happen quite often. And now we're going to use that information to check to see, is the current millis greater than the previous millis plus the period that we mentioned before, right? Has enough time elapsed in combination with when we last ran this to run it again. And we will only go into this block every 50 milliseconds or longer, because remember, depending on what else is going on, there's no guarantee that we're going to check this exactly at 50 milliseconds. If some other function was running that took a lot of CPU time and the 50 milliseconds elapsed, and say we went to 60 milliseconds, well, this will still be valid and we will still run this code, albeit 10 milliseconds after the minimum amount of time that has to pass. Also keep in mind that we have to, as part of this, set the previous milliseconds. So it's good to kind of do that now, just before I forget. So I'm going to set that equal to the current millis at the end, and you want to do that at the end of this block. So now that we have that set up, we can actually use this code to do some checks and to look at the encoders. So let's do that. The first part of looking at the encoders is again going to be setting up a couple of variables. Now I'm going to actually set these up globally, but they don't need to be, especially in this example. I could actually run all this code right within this method, but commonly in these kinds of things, you're going to be using the results of this in other places, say in a function that deals with using the motors, maybe in some of your other functions that deal with the actual mathematics, localizing the robot. I'm going to create one called counts left. This is going to be the variable that we're going to put that into for the left wheel, and counts right for the right wheel. And I'm also going to use, again, a previous counts. So I'm going to say previous left and previous right as well. Now that we have those, we can come down here and we can assign them. And remember, I don't want to reassign. I want to add on every time, right? So if I get an encoder count in one iteration of this, 50 milliseconds or more later, when I come to the second iteration, I don't want to overwrite this. This is the total count. I want to add to it. So this is the equivalent, we say plus equal. This is the equivalent of saying counts left equals counts left plus whatever I'm going to add to it. And what I'm going to add to it is the value I get from the encoders. So we say encoders dot, the method I actually want to use is get counts and reset left. Now, the reason why I want to do this is there's only a limit, I believe it's 32K or 32,000 on the register that keeps track of the encoder as it goes. That actually overflows pretty quick. So in a turtle that has a 75:1 gear ratio, I want to say it's like 30 seconds, depending on the speed of the motor, of course, but it's not very long. You're going to want to reset this often, and you're keeping track of the count in your longer long, right? So there's no reason to really not reset it often. So every time I retrieve the value, I reset the register so that I'm less worried about it overflowing in the future. I'm going to repeat this for counts right. And now that we have that information, why don't we just simply print it out? So we're going to do serial print, and we're going to do left. Let's do another serial print here. We're going to have the counts left and one more here. Now I mentioned earlier concatenation doesn't really work in this, so this is how you effectively do that. And then in the last line, we go ahead and put our println. Now, also want a space there or it'll look funky. And here is our counts right. Okay, so let's see if this compiles. Let's see how the demo gods feel about me. Previous millis not declared. I called it priv, that's why. So let's take the IOUS out, same thing. And let's try again. All right, looks like we're gonna go that time, and we did. All right, so we're going to compile and run. Let's open our serial monitor here. And there you go. You can see our left and right coming up as zeros. Now, of course, I haven't applied any motors. I took that code out. So I'm going to physically move the robot, and you can see that they are, in fact, one of them is going up. And notice the other isn't, because after giving that whole speech about adding, continually and not replacing, I didn't do it for the right one. So let's reset that and do it again. And there you go. That's much better. All right, so I'm just moving it back and forth. You can see if I move it back further that I go into negatives, and if I move it forward, I stay in positives. So That's great. So we've accomplished one goal. We've accomplished reading the encoders and being able to display that out. And just to play around a little bit here, let's change the period so we can kind of get a feel for how fast that is. Let's change it to 500 just so you can see the difference, and we'll upload that, come back over here, and let's clear this just so we can see it fresh. And now you see every half second it's updating. And look at how much of a lag that is. I mean, if you imagine that I had gone past a certain distance, you can see that quite a bunch of clicks happen in between. And I mean, I'm not even pushing this thing very far, very fast. And this is a standard edition, not the Turtle. The Turtle numbers would be more than twice as fast as these because of the gear ratios. Just something to keep in mind. Again, that period is very important. I'm going to put it back to 50 milliseconds. Let's reset that, reset this to clear it. And again, you'll see the difference right away because this is going to scroll right off pretty quickly. Now that we have the encoder, let's learn the math that we need to actually convert that into distance. We're going to convert it into distance in centimeters. So to convert it into distance in centimeters, we're going to need first two variables, which I want to be floats because these could be fractional numbers. So we're going to call them SL for the distance traveled by the left wheel and SR for the distance traveled by the right wheel. So now that we have our SL and SR to keep track of wheel rotation, let's add a few more constants that we're going to need here. I'm pasting these in and I'm going to go through each one at a time. So the first one here is clicks per rotation. Now this is specifically referring to the rotation of the DC motor and the encoder shaft. This is every single time the DC motor makes one full rotation, there are 12 state changes acknowledged by our encoders. Now, that is not the clicks per rotation of our wheel. Remember that our DC motors have a gear mechanism to actually slow down the DC motor's rotation and increase the torque. The standard edition that I'm using is a 30:1 gear ratio. Now, the very specific, as shown on the data sheet here, gear ratio is actually 29.86. If you have the Turtle edition, this is actually I believe 75 point something, and the Hyper edition is even slower than this one at 15 point something. That means that the Turtle edition actually shows the most clicks because you've slowed down the wheel and increased the number of clicks that happen at the shaft of the DC motor before the wheel fully rotates. The slower the robot goes, the more clicks you get per rotation. The combination of these two things, when we multiply them out, give us the total number of clicks that happen for the encoder per wheel rotation. The next thing we need to know is the diameter of our wheel and the circumference of our wheel. Now we know that the circumference of our wheel is the diameter of our wheel times pi. The diameter of our wheel we can luckily look up, as seen here, using the Pololu documentation. So it's a 32 millimeter wheel. We are going to be using centimeters. So once we have our wheel diameter, we can figure out our wheel circumference. So now that everything is set up correctly, let's paste in the equations that we'll be using here and disseminate what's going on. I want to start with inner parens first. So the first thing I want to note here is that we're getting the difference of the counts. So remember, just the difference that happens each time we come and pass this period and check. We're going to be dividing that by what happens in here. This, remember, is the clicks per rotation of the actual DC motor times the ratio of the gears, giving us the rotation or the clicks per one rotation of the entire wheel. We're then going to multiply that by the wheel circumference. The total result of this is divided by the actual number of clicks, which gives us the distance achieved in that number of clicks. That's what you're going to find in here in centimeters. This is obviously the same exact thing for the right-hand side. Let's go ahead and change these values out here so we can see what we're looking at. Let's do a compile and a load, and let's go to here And you can see here that we now have left and right with floats, and let's see what happens when we move them. Look at that. Now we actually see the centimeters, and I'm going to move it, I went over, about 12 inches, and that is about 30.5 centimeters. And that is how far we're going to now tell the motors to move it in the very next section. So this is very good. Now we have it measuring distance, but we just need to use the motors to now try to go a certain amount of distance. Let's give ourselves some space here and take a look at the code we're going to be bringing in this section. So what I've done here is essentially just create a integer variable to contain the wheel speed, which I've set at 200. I could have just written 200 here. However, I might want to change it, so this made my life a little bit easier. This is important. Notice here what I'm doing. I'm saying if SL is less than 30, I'm going to set the motor speed to what I said here. And otherwise, I'm going to stop. Well, that seems pretty straightforward, and it's correct for what we're doing here in Arduino. But I want to point this out because most people would probably be inclined to do a while loop here or some kind of for or some looping mechanism. We have to consider though what would happen if we had done that. Remember, if we're in a while loop here, this SL value is not going to get updated because we're never running this code while we sit in this loop. So this breaks what we want to achieve, and this is a very common problem when you're dealing with microcontrollers, and in particular Arduinos. Remember, you are in a loop. If you find yourself wanting to create a loop, consider instead, what is the condition that I would check in this loop, and can I instead just use an if statement and the existing loop that I'm already utilizing as the looping mechanism. So here I am simply implementing that condition to say, while this SL is less than 30, let's go forward. Otherwise, we're gonna sit still. Let's go ahead and see how this runs. Now, be aware when you do this, your robot is going to be moving, and if you have a bug or something, maybe more than you expected, so hopefully it's afoot, but just be aware and ready to catch it when it starts moving. Let's hit upload. And we'll see our speeds here, clear the output, and make sure to turn your motors on, and boom, it went and it stopped. I'm gonna do it again here. Let's clear our output and run it one more time. And there you go. Now, notice that we are getting a little bit more than the 30 we expected. In fact, I do want to point out here that I said it was precisely 30.5, and we didn't actually do that. So let's be more precise, shall we? But that's not going to fix our problem. In fact, let's just go ahead and upload this and see what happens when I do. And the answer is that we still got even a little bit further than we thought. Now, if you remember when we discussed the amount of time that we had here in our period, we said that something like this might happen, that we might not check our code often enough in order to respond quickly. Let's see what happens if we drop it down to 10. That was pretty consistently reading in the 35, 36 range. Let's see what happens now. Oh, better. Not perfect, but better. So this is a great example of things you have to watch out for. Just out of curiosity, let's take this all the way down to a period of 2 and run it one more time. So we definitely had a better result that time. And there's about as good as we're gonna get. Now, I know another reason why this is failing, and it actually is not the period. And this is important because you could struggle with this and say, well, you know, what's going to happen now? I can't actually lower the period effectively anymore. It's not 2 had no difference from 10. In fact, let's bring this up to 20 and see if it even makes any difference at all. This is a good time to try to figure out, tuning wise, what is the period that I need to be as precise as I do. And the result for 20 is exactly what the result for 10 was. So 20 appears to be a good number. Let's stick with that. But we're definitely further than we want to be. I mentioned earlier that a large portion of the effort and what makes robot programming unique is tuning it for the real world. And we've now seen that just in looking at how quickly we update mechanisms that read the encoders and how quickly we pull distances from there have a real effect on how precisely we can come to meeting our goal. Now, another big thing that's going to have a factor is speed. Now, I guarantee if I lowered this speed right now, right off the bat, it would actually improve our situation, but it's still not going to get us precisely where we need to be. And the reason for that is because you might have noticed my pretty quick standard edition here, moving at half speed, actually makes an audible thump when it gets to the end, because the back end is actually flipping up and it's moving forward a bit further than it should. Imagine getting in your car and driving at 60 miles an hour and effectively trying to stop instantly. That's not going to happen. Now, obviously our robot does not have the physical weight of a car, but it still has to deal with this problem. Now, this problem I'm describing, I mentioned earlier, is known as the dynamics of the robot. And we can try to overcome that here, maybe by slowing ourselves down as we approach the finish line. So more to make the math easier, and also to make this more controlled, because you don't just get to go as fast as you want for free. If you want precision, you might have to slow things down. I'm first going to slow the robot down, but that alone isn't going to be enough. What I'm then going to do is add this code here that's going to slow us down right as we approach the end. Now, what's going on here? So I have another if check here where I'm now looking to see, well, we're in our less than 30.5, but are we greater than 20? Because if we're not, then I'm just going to go ahead like normal and work at my normal working speed. So for the first 2/3 of this trip, my robot is going to continue on its merry way just like it was before, albeit now at half the speed. However, when I'm now within 10 centimeters of my goal, or 10.49 to be exact, I'm going to start reducing my wheel speed. Look at what we have here. So I'm taking the difference here of the actual encoder value and 30. So I'm saying, what is my actual difference from 30? If I hit this loop and I was at 21, let's subtract that from 30 and see that I have 9 centimeters left to go. I'm then going to divide that by 10, so I end up with 0.9, and I'm going to multiply it by 100 to actually reduce my speed to 90. So you can see as this goes, as I'm 8 centimeters away, my wheel speed should be 80, 70, etc., right? This is going to keep going on. This next line now is to deal with the fact that my robot needs a certain amount of power to keep its wheels turning. If I go all the way to 0, it is actually likely that my robot might fall short of its goal because it doesn't have enough torque to keep itself moving. So to try to prevent that, I'm going to reduce my wheel speed to 20. But if it goes below that, if I was, say, only 1 centimeter away here at 29 centimeters, this condition here would automatically keep the wheel speed at 20. It will not go below that. I think this is going to have a good effect, but let's go ahead and see. And I want to point out that this may require some tuning. If you have a Turtle Edition or Hyper Edition or any other type, even if your DC motors are different from mine, if your robot weighs more than mine, any factors can change this. You might have to insert your own values. These numbers might not work precisely for your robot, but the idea will. All right, let's go ahead and see how this works. Check that we can compile, and we can. Let's go ahead and load it up. Look at that, pretty close. Now notice the right went a little further than the left. I still have the tether in. Since I don't have to reflash, I'm actually going to remove the USB cable and see if that happens again now without it. So I'm resetting it now. Obviously the serial monitor won't show the difference, and that looks pretty clean. Let's go ahead and put this next to the measuring tape and see how we do. Congratulations on completing the very first lab in the series. I would like you to think now about how you can take what we've learned here now and apply it more broadly. What if your robot wanted to travel faster than 75 out of 400? What if it was traveling any distance, going to a goal where you didn't actually know exactly how far it was going to be away when the robot started? Perhaps you can use it to have your robot navigate a predefined path around your house. Leave me comments. Let me know how you've improved this algorithm, used it, and refined it. Thanks for joining me in this very first video in the Robotics Lab series. If you like this content, please subscribe. I will be adding new videos to this one, so we're going to be doing PID controller, and we're going to be working up to potential fields and path planning. There's going to be a lot more coming. Please do check those out. No robots were harmed in the making of this video.